In this video, we're going to take a look at Bayes' theorem. Bayes' theorem allows us to calculate conditional probabilities that are a little more complex. One criteria for Bayes' theorem conditional probabilities is that the outcomes of event 1 must all be mutually exclusive. Bayes' theorem is this very long formula. And I'm going to take this formula that's provided in your textbook and typically online and show you that it can be simplified a great deal. So we know that the probability of B sub 1 given A is equal to this long formula. And let's first start by figuring out what they are meaning at each step. So here in our numerator, it tells us the probability of B sub 1 multiplied with the probability of A given B sub 1. Okay, so we've got that piece, and then it's duplicated down below. And then we have added on to that another probability of B sub 2 multiplied with the probability of A given B sub 2. Now B sub 1, B sub 2, B sub 3, and B sub so on are all the outcomes that event 1 could possibly have. And so these different sections are trying to say, here's the probability of A for the first outcome in event 1. And here's the probability for A in the outcome 2. Here's the probability of A in outcome 3, and so on. And so we can use a conditional probability formula that we've encountered before to help us recognize that the probability of B sub 1 multiplied with the probability of A given B sub 1 is really the probability of their intersections. So then I take all of the work up above and I replace it with intersections. So the numerator is the probability of B sub 1 intersect A. And in the denominator, we have the probability of B sub 1 intersect A, and then B sub 2 intersect A, B sub 3 intersect A, and so on. All of these in the denominator, when we add those together, actually creates the probability of A. So once again, this right-hand side brings us back to the true definition of the conditional probability that we've used before. But this long extended denominator allows us to look at situations where the event 1 could have more than one outcome. Now let's connect this to a tree diagram. From prior work, a tree diagram allows us to say that this event 1 has the 4 outcomes, B sub 1, 2, 3, 4, and this could be extended infinitely. And then I chose off of each outcome to say that the next event could have 2 outcomes, A and C. In reality, there could be multiple outcomes. And we know that the second branch is the probability of A given the first event B sub 1 occurred. And then the second branch down below is the probability of A given B sub 2. And if we multiply branches together, we find the intersection of the first event with that second event A. Okay, so because we know we could multiply our various branches to get our intersections, that helps us because now we can take all those intersections that involve A, we can add those together, which is what this denominator is really doing, and say, hey, that's really the probability of A. An example may help us understand Bayes' theorem further. This problem says the enrollment in a course is 0.1 first-year students, 0.3 second-year students, 0.4 third-year students, and 0.2 fourth-year students. Experience has shown that the likelihood of receiving a B in the course is 0.2 for first-year students, 0.3 for second-year students, 0.4 for third-year students, and 0.1 for fourth-year students. Find the probability that a student who receives a B is a second-year student. Let's begin by starting with a tree diagram. We have first, second, third, and fourth-year students with the probability of 0.1, 0.3, 0.4, and 0.2. Then it talks about receiving a B. A first-year student receives a B 0.2%, or sorry, 0.2, which is 20%, and not a B, the rest. Second-year students, 0.3 and 0.7. Third-year students, 0.4 and 0.6. And four-year students, 0.1 and 0.9. When we multiply the branches that extend from the beginning all the way to the end, we're finding our intersections. So this 0.1 times 0.2 is going to be 0.02, and it represents the probability of first-year students and receiving a B. I'm only going to focus on the probabilities where students get Bs. So for second-year students, we're going to have 0.3 times 0.3, which is 0.09. Third-year students, 0.4 times 0.4, which is 0.16. And four-year students is 0.02. If we add these probabilities together, we're going to find the probability of getting a B. Let's see, 0.02, 0.09, 0.11 plus 0.16 is 0.27, 0.29. So the probability of getting a B in this class is 0.29. And it said, find the probability that a student who receives a B is a second-year student. So probability, second-year student, given that they got a B. That means we want to find the probability of the intersection of a second-year student with B and divide that by the probability of B. Now, with all the work that we did, we can see that the intersection of a second-year student getting a B was 0.09. And the probability of getting a B was 0.29. When we divide these, we will find out the probability of a second-year student getting a B is 0.31.